we introduce our paper, Detection-Based Part-Level Articulated Object Reconstruction from Single RGBD Image. Estimating object shape, pose, size, and kinematics from a single frame of partial observation is a fundamental challenge in computer vision. Understanding such properties of daily articulated objects has various applications in robotics and AR, VR. Shape reconstruction of daily articulated objects is a challenging task. These objects exhibit a range of shape resulting from different local part poses. More importantly, they display significant intra- and inter-category diversity in part configurations, including variations in part counts and structures. These factors together contribute to an exponentially increasing shape variation. To address this challenge, we propose an end-to-end trainable detection-based approach for part-level shape reconstruction of articulated objects. Given a single RGBD image with an optional foreground mask, our model outputs part shape, pose, joint parameters, instance category, and parts to instance grouping. Previous works first detect each instance and then reconstruct a target shape by primarily employing ASDF architecture for shape learning. In ASDF, a shape decoder outputs the entire shape of the instance from instance-level latent space. However, this approach is limited when dealing with varying part counts and structures, as the shape decoder must handle an exponentially increasing number of shape variations due to different part layout combinations, in addition to local part poses. Consequently, addressing this variety with a single model remains a complex and unsolved task, as previous works assume fixed part counts per model. In this paper, we address this complexity through our novel detecting group approach. Our key observation is that the daily articulated object shape can be decomposed into multiple part shapes. This approach first detects a set of part features and decodes them into part attributes and part shapes. Then, parts are grouped into multiple instances based on grouping embeddings trained as a metric learning. In this way, we provide a scalable and generalizable approach for handling diverse part configurations of daily articulated objects in a scene. Building upon 3-DETER as a transformer-based detector backbone, we train our pipeline end-to-end from part level to instance level estimation, including shape reconstruction in a single stage. Articulated objects often consist of small and thin parts. We can increase the number of queries at test time to address this issue. However, simply adding more queries results in severe false positives. This is because standard IOU metrics use overly small values for thin structured parts, even when they approximate. To overcome this challenge, we propose a post-processing step called kinematic part fusion, KPF in short. We employ a novel IOU score, termed kinematics-aware IOU, KIOU in short, based on the observation that the redundant part pair exhibits significantly overlapping trajectories. We construct a convex hull for each part using 3 bounding boxes of different part poses. We further propose to fuse the part proposal in terms of all estimated attributes based on KIOU to improve the performance. We employ KPF during inference as shown in the pipeline. To the best of our knowledge, there is no suitable off-the-shelf dataset for the setting in which a single scene contains multiple articulated objects with various part counts. Therefore, based on the Sapien dataset, we have built such a dataset with photorealistic rendering for the evaluation. Our method significantly outperforms the baseline method in reconstruction quality and is able to reconstruct the articulated object with diverse part configurations. Our method is also able to estimate the accurate kinematic parameters, enabling articulatable shape reconstruction. Although only trained on the synthetic dataset, our method reasonably generalizes to the real data from benchmark dataset and in-the-wild images taken by smartphone. By using the KPF, we show it improves the reconstruction quality by improving the detection of far small parts in the scene. We propose end-to-end trainable part-level shape reconstruction method for variously structured articulated objects. We propose novel detecting group approach for handling various articulated object structures. We also propose kinematic part fusion to improve the reconstruction quality, suppressing the false positives. Our method reasonably generalizes the real data while only trained on synthetic dataset. Thank you for listening.